Dear students, in this video I will discuss about UV visible spectroscopy. The important region of absorption, the theory of absorption, characteristics of UV visible spectra, important electronic transition, important terminologies as chromophores and oxychrome, or what are chromophores, examples, what are oxychrome and their examples, and absorption and intensity shifts such as bathochromic shifts, hypsochromic shifts, hyperchromic and hypochromic shifts, etc. Okay? UV visible spectra is originated by the absorption of radiation by the molecule from UV visible region of electromagnetic spectrum that comprises 200 nanometer to 800 nanometer. Among these, 200 nanometer to 400 nanometer comprises UV region, and 400 to 800 nanometer comprise the visible region. Okay, electronic transition takes place from lower energy ground state to higher energy excited state when a molecule absorbed UV visible radiation, right? See, the UV region below 200 nanometer is usually referred to as vacuum UV region because the air present in the spectrophotometer containing oxygen, it absorbs below 200 nanometer wavelength, and hence the spectrophotometer has to be evacuated. Thereby, such a spectroscopy is known as vacuum spectroscopy. But this vacuum UV spectroscopy gives a limited information, and hence usually organic chemists are not much interested in vacuum UV spectroscopy, right? As the electronic transition takes place during the absorption of UV visible region, most often the UV visible spectroscopy is referred to as electronic spectroscopy. See, after the absorption of light in the UV visible region, a UV visible spectrophotometer records a UV or visible spectrum as a plot of wavelength of absorbed radiation versus the intensity of absorption in terms of absorbance or optical density A, or molar absorptivity, that is otherwise called molar extinction coefficient epsilon, as defined by the Beer's and Lambert's law, or Lambert's and Beer's law. It is represented as log I0 by I, that is equal to A, that is Lambert and Beer's law. A is otherwise equal to epsilon into C into L, where I0, here I0 is the intensity of incident radiation, and I, the intensity of radiation transmitted through the sample solution. A, the absorbance or optical density. Here epsilon is the molar absorptivity, otherwise called the molar extinction coefficient, and C is the concentration of the solute per moles per liter, usually per moles per liter or in moles per liter, and L is the path length of the sample, usually in centimeter. Okay, here it is the UV visible spectrum. Here lambda max is the molar absorptivity at the maximum absorption of wavelength, lambda max, or it is the lambda max, that is the wavelength of maximum absorption, that is maximum molecules absorbed this wavelength, maximum number of molecules absorbed by absorbed this wavelength. Here it is the intensity factor, that is epsilon max. It indicates how many or what percentage of molecules are absorbed this wavelength. It is the wavelength of maximum absorption. Maximum number of molecules absorbed this wavelength, and it is represented as lambda max. Okay. See, instead of getting discrete lines, the UV visible spectra is usually obtained as absorption band or broad band. It is because the energy required to induce an electronic transition is larger than that required to cause transition in the accompanying vibrational and rotational levels. See, each of the electronic level consists of or accompanying vibrational and rotational levels. And if we pass UV visible radiations to the molecule, usually the electronic transition is usually accompanied by the transition in vibrational and rotational levels. Thus, electronic absorption is superimposed upon the accompanying vibrational and rotational absorption, resulting in the formation of broad band. And so you will get absorption band instead of getting discrete line or line spectra. Okay, you can see this diagram shows the possible electronic transition, that is from pi to pi star transition, followed by the vibrational transition, and rotational transition takes place in ground state to pi molecular level and pi star molecular level. You can see the vibrational transitions from the ground state to excited state, and also rotational transition from the rotational levels of ground state to excited state. And so these transitions are accompanied usually by, along with the electronic transition. These causes that we had discussed to obtain absorption band instead of discrete lines. Okay, and so we can say UV visible spectra is obtained as broad spectrum. So we had seen that UV visible spectra is obtained by the electronic transition from ground energy levels to higher anti-bonding excited level within the molecule. See, what are the important electronic transitions usually taking place in an organic molecule? That is important in UV visible spectroscopy. See, the important molecular energy levels within an organic molecules are sigma, pi, and non-bonding molecular orbital. Sigma and pi molecular orbitals are associated with its anti-bonding molecular levels as sigma star and pi star. Sigma star and pi. Pi has its corresponding anti-bonding molecular level, pi star. But non-bonding molecular orbital will not have such anti-bonding level, because non-bonding molecular level or non-bonding molecular orbitals usually do not take part in bond formation. Okay. See, this sigma to sigma star excitation or transition requires highest amount of energy. It absorbs highest amount of energy for this transition, sigma to sigma star. Then comes the n to sigma star transition, which requires energy usually less than sigma to sigma star transition. And then comes pi to pi star transition, which usually having lower energy than n or which requires lower energy than n to sigma star transition. Then n to pi star transition, another type of transition which requires the least amount of energy. Okay, let us discuss a little bit more about each of these transition and about what are the information given by each of these transition. First, the sigma star transition. It is obtained by the promotion of an electron from a bonding sigma molecular orbital to an anti-bonding sigma star molecular orbital. It requires very high energy because sigma bond is strong. Sigma bond is strong. So this transition requires a very high amount of energy. And hence these transitions usually do not occur in normal UV visible region. You know, normal UV visible region is 200 to 800 nanometer. This energy is greater than this region and hence absorbs below 200 nanometer for this transition. Alkanes and compounds with only single bonds or only single bonded compounds gives these transitions. Alkanes, for example, absorbs around 150 nanometer. For example, ethane absorbs a lambda maximum of 135 nanometer. Usually the region below 200 nanometer is called vacuum UV region. Vacuum UV region. Since oxygen is present in the air, absorbs strongly at around 200 nanometer and below. You know, below 200 nanometer, there is air in the spectrophotometer and hence it has to be evacuated because air containing oxygen and this oxygen absorb below 200 nanometer or around 200 nanometer and hence it has to be evacuated and hence this region is called vacuum UV region. But vacuum UV region do not give much information about the structure of molecule and hence organic chemists usually do not give much interest in vacuum UV region or vacuum UV spectroscopy. Okay. Another important transition given by organic molecule is N sigma star transition. That is transition of an electron from a non-bonding orbital to an anti-bonding sigma orbital. That is N sigma star transition. That is from non-bonding molecular orbital to anti-bonding sigma star molecular orbitals. Usually compound containing non-bonding electrons on heteroatoms are capable of showing absorption due to this transition. Compounds containing non-bonding electrons on heteroatoms like halogen, nitrogen, oxygen, sulfur, etc. showing this type of absorption due to N sigma star transition. Usually this transition requires lower energy than sigma star transition. You know, sigma star transition requires highest amount of energy among the electronic transition. But N to sigma star transition requires lower energy than sigma star transition. Examples: halides, alcohols, ethers, aldehydes, ketones. All these molecules containing non-bonding electrons on heteroatom and hence take part in N to sigma star transition. For example, you can see in methyl chloride the lambda maximum of N to sigma star transition is 173 nanometer, whereas in methyl iodide it is 258. In methyl alcohol there is also oxygen atom heteroatom which containing non-bonding electron and hence there is possibility for N to sigma star transition gives a lambda maximum of 183 nanometer. In water the lambda maximum is shown 167 nanometer where there is heteroatom oxygen in which non-bonding electrons are present. Okay. See, the electronegativity difference on of the heteroatom of the molecule is usually affects the wavelength of absorption in UV visible spectroscopy. For example, you can see in the case of methyl chloride the lambda max is 173 while in the case of methyl iodide it is 258 nanometer. This difference is due to the electronegativity difference between chlorine and iodine. Chlorine having more electronegativity, the electrons in the non-bonding molecular orbital is tightly or strongly binded with the nucleus and hence it is very hesitant for the excitation process and hence N to sigma star transition requires more energy or lesser lambda max value for excitation, that is 173 nanometer. Correspondingly, its epsilon maximum also getting decreases to 100. You can see the epsilon maximum is 100 in the case of methyl chloride. Whereas in the case of methyl iodide, iodine is lesser electronegative than chlorine and hence its non-bonding electron is not tightly binded, and hence it gets excited to sigma star transition easily, and hence energy gap getting decreases, thereby lambda max or wavelength of absorption increases compared to methyl chloride, that is to about 258 nanometer. You can see the corresponding value of intensity of absorption or epsilon maximum, that is 378. Okay. Then similarly, in the case of methyl alcohol and trimethylamine, you can see methyl alcohol having a heteroatom oxygen which is more electronegative than nitrogen of trimethylamine, and hence it absorbs or it requires high energy in order to transit from N to sigma star, thereby its lambda maximum is 183, less than that for trimethylamine, where nitrogen is the heteroatom which is having lesser electronegativity than oxygen atom. See this difference of in lambda max and epsilon max when there is heteroatoms with electronegativity difference. Okay, if you protonate this trimethylamine with an acid, there will be no longer the presence of non-bonding electron, and hence we cannot see the N to sigma star transition in protonated trimethylamine. Okay. Another important type of electronic transition taking place in organic molecule is pi-pi star transition. Pi-pi star transition. It is usually occur in compounds containing one or more covalently unsaturated groups like carbon-carbon double bond, carbon double bond oxygen, nitrogen double bond oxygen as in nitro group, etc. See, pi-pi star transition requires lower energy than N to sigma star transition. We had seen pi-pi star transition requires the lowest, a pi-pi star transition requires lower energy than N to sigma star transition. For example, in unconjugated alkenes, if there is no conjugation, this transition occurs in the range of 170 to 190 nanometer. That is, N to sigma star transitions requires 170 to 190 nanometer in the case of unconjugated alkenes. For example, ethylene shows the lambda maximum of 171 nanometer. Ethylene shows the lambda maximum of 170 nanometer. Similarly, unconjugated carbonyl groups show pi-pi star transition in the range of 180 to 190 nanometer. 180 to 190 nanometer. You can see in the case of acetone, where there is pi-pi star transition in carbonyl group, it shows 188 nanometer. 188 nanometer in acetone, where there is carbon double bond oxygen. Okay. Another important electronic transition takes place in organic compound is N-pi star transition. N to pi star transition. N to pi star transition requires lowest amount of energy among the electronic transition. It requires lowest amount of energy among the electronic transition. Usually carbonyl groups shows this type of transition. Carbonyl groups shows this type of transition. For example, you can see saturated aldehydes and ketones show both the pi-pi star and N-pi star transition. See, both this containing C double bond O group and this C double bond O group containing pi bond and a sigma bond, and also non-bonding electron in the hetero atom oxygen, and else we can expect this transition as pi-pi star transition and N-pi star transitions in aldehydes and ketones. Usually pi-pi star transition in these compounds or carbonyl group usually occurs between 180 to 190 nanometer, and N-pi star transition occurs between 270 to 300 nanometer. You know, carbonyl compounds, because having these non-bonding electrons, also exhibit high energy and sigma star transition around 160 nanometer. For example, in the case of acetone, it shows a lambda max of 166 nanometer because of n sigma star transition. Okay. Now let us consider some of the important terminologies come across during the study of UV visible spectroscopy. One important terminology we have to know is chromophore. You know what is chromophore? It is actually unsaturated groups responsible for absorption in UV visible region. These are the important groups which are responsible for the absorption of UV visible region. All these you can see are unsaturated groups: carbon-carbon double bond, carbon-oxygen double bond, nitrogen-nitrogen double bond, carbon-carbon triple bond, carbon-nitrogen triple bond, and you can see in nitro group there is nitrogen-oxygen double bond. Compounds with these chromophores, this type of chromophore absorbing visible region, that is 400 to 800 nanometer, are usually colored. If a compound absorbs this region 400 to 800 nanometer, then that compound is usually appear to be colored. Okay. Then oxochrome. What is oxochrome? It is actually a covalently saturated group which attached to chromophore, which changes both the wavelength and intensity of absorption. Because of the presence of these groups, it changes the wavelength of absorption and intensity of absorption because of the presence of oxochrome. For example, NH2 group, OH group, and SH group, also halogens, etc., all are covalently saturated group. But when these groups attach to a chromophore, the wavelength of absorption and intensity of absorption also changes because of the presence of these groups, and such groups are represented as oxochrome. Right? For example, see these examples: benzene and aniline. The lambda max of benzene is 256 and epsilon max 200, whereas in aniline these were lambda max 280 and epsilon max 1430. See, when NH2, the oxochrome, attached to benzene ring, the lambda max of benzene gets shifted from this 256 to lambda max of 280 in aniline. That is, this oxochrome NH2 increases the lambda max of the chromophore benzene ring to about 24 nanometer, increases to about 24 nanometer. Similarly, you can see the shift in lambda max, epsilon max also. It gets increased from epsilon max 200 in benzene to 1430 in aniline. Okay. Usually oxochrome increases a value of lambda max as well as epsilon max through extending the conjugation through resonance. You can see in this case, aniline, the NH2 group having a lone pair of electron in nitrogen, which will contribute for the resonance, and hence extension of conjugation takes place through the resonance by contributing this non-bonding electron to the resonance of benzene ring. So that extension of conjugation takes place, thereby there will be an increasing the lambda max value and also epsilon max value. Okay. This type of shift of absorption maxima to a longer wavelength due to the presence of an oxochrome or solvent effect is usually referred to as bathochromic shift. And so bathochromic shift is the shift of absorption maximum to a longer wavelength due to the presence of an oxochrome or solvent effect. For example, in the case of aniline having lambda max 280, but benzene having lambda max 256. By the presence of this oxochrome NH2, the lambda max or shift of absorption about 24 nanometer from benzene to aniline because of the presence of this oxochrome. Solvent effect can also change the absorption maximum. For example, lambda maximum of acetone is 264.5 nanometer in water, that is polar solvent. But in nonpolar hexane, it is found to be 279 nanometer. That is bathochromic shift of about 14.5 nanometer, about 14.5 nanometer is caused by polarity change. Okay. Sometimes there will be a shift in absorption maximum to a shorter wavelength, usually caused by the removal of conjugation or change in the solvent polarity. For example, if we add acid to aniline gets protonated to form anilinium ion. This anilinium ion no longer contains the lone pair of electron or non-bonding electron on nitrogen. That is why the conjugation is lost in anilinium ion, and hence its lambda maximum is reduced from 280 in aniline to 254 in anilinium ion. Okay. This type of shift of absorption maximum to a shorter wavelength caused by the removal of conjugation or change in solvent polarity is known as hypsochromic shift. See, for example, a shift of 10 to 20 nanometer in the lambda max of pi star bands of carbonyl compounds on going from ethanol as solvent to hexane. That is, on decreasing solvent polarity, there will be a shift of lambda max in pi star transition of about 10 to 20 nanometer from ethanol to hexane. Ethanol is polar solvent. If we change this to hexane, carbonyl group shows the pi star absorption at a lambda maximum by decreasing lambda maximum around 10 to 20 nanometer, or in between 10 to 20 nanometer. There will be this much amount of decrease in absorption maximum. That is, hypsochromic shift is seen. Right? The terminologies related to absorption intensity epsilon max is hyperchromic shift and hypochromic shift. Hyperchromic shift is an effect that leads to an increase in absorption intensity, epsilon max. For example, introduction of NH2 group in benzene shift the epsilon max from 200 of benzene to 1430 in aniline. Here NH2 group, the oxochrome, increases the absorption intensity epsilon max from 200 to 1430 when benzene changed to aniline. This much amount of increase because of the presence of NH2 group. Okay. Hypochromic effect is an effect that leads to a decrease in absorption intensity epsilon max. A decrease in epsilon max. That is hypochromic effect. That is the effect that leads to an increase, a decrease in absorption intensity epsilon max. For example, Introduction of a group which distorts the chromophore causes hypochromic shift. In biphenyl, the lambda max is 252 nanometer and epsilon max is 19,000. Epsilon max is 19,000. This epsilon max 19,000 gets decreased to epsilon max of 800 when two methyl groups are attached to the ortho and ortho dash positions or 2 and 2 dash positions of biphenyl. See, for example, in biphenyl, epsilon max is 19,000. In 2 dash dimethyl biphenyl, epsilon max is 800. This much decrease from 19,000 to 800 is observed because of the presence of this methyl group. This methyl group at this position, methyl groups at this ortho and ortho dash position or 2 dash position distort to the symmetry of biphenyl because of the bulky methyl group. Steric hindrance causes the distortion of planarity of biphenyl again, and which causes the decrease in epsilon max from 19,000 to 800. Okay. Yes, in this video we had discussed the important electronic transitions, characteristics of these transitions, important terminologies such as chromophores, oxochromes, bathochromic shifts, hypsochromic shifts, hypochromic shifts, and hyperchromic shifts, etc. With this, I conclude this video. In the next video, we will discuss what are the important factors that affects the wavelength of absorption and intensity of absorption. Okay, thank you.